Welcome everyone, and thank you very much for joining the May workshop. As you know, my name is Talia, and I'm delighted to have you at the tamtechacademy's the next workshop. And today's session is dedicated entirely to separation processes. It is, as you know, one of the most fundamental and far-reaching topics in chemical and process engineering. And I'm literally sure that at every university, it is part of the curriculum, and you got some previous knowledge as well. So starting with that, please mention in the chat which types of separation knowledge that you got during university and which classes did you know. So, and I can start my presentation. As a hook, I would say that think about this for a moment, like virtually every product we use every day, for example, fuel in our cars, the medicines that you take, or even clean water that we drink, it exists everywhere because someone, somewhere, they built a process to separate one substance from another one. And that's why separation is the backbone of the process industry. And we say that it is one of the most frequently asked questions. It comes from the separation topic. Let me take my pointer. We will start with, first of all, some separation techniques, some basics of separators, and how we handle the multiphase fluids. And we'll go through especially the science of distillation. Then we will somehow focus on contrast between absorption and adsorption as well. And by the end, you will have some solid framework for understanding why we choose one separation techniques on the other one, and how they all fail if we are not carefully, especially in the industry. And as a reminder, so you can ask your questions at every part of the session, or you can ask your questions at the end. I'll flag the polls for discussion as well. For the separation techniques on the Google, you will see out such, let's say, the picture. It will start with distillation, and it will list down at least 20 techniques that you have to be aware of this. In general, why it matters, why we have to know the separation processes, because in oil and gas industry, for example, what comes out of a wellhead is rarely a single clean product, and you can get complex cocktail like crude oil, produced water, dissolved gas, sand, sometimes CO2, hydrogen sulfide, or some other impurities as well. And every one of those, they have to be separated before anything can be sold, transported, or safely disposed of. So now using this, because in general separation could be categorized in different ways. For example, if I broaden in the categories, it could be like the first one is mechanical separation. We use some physical differences like density, gravity, phase to split the streams. Or here the separators and scrubbers fall into this category that you know, the distillation as well. But the second one could be the mass transfer based separation techniques. I would put here the thermodynamic properties, volatility differences, solubility differences, and to drive components between phases. So let me ask this question now. So in your opinion, what is the distillation based on? Which physical maybe difference, or let's say thermodynamic property that you know it is based on? Sabina?
Distillation works according to the difference in the boiling temperature. So that will be the main force for that distillation process.
What else? Like considering the driving force that you mentioned.
We can also say that volatility we can see.
Yes, exactly. Yes, relative volatility we can also mention. It also comes from sometimes the difference in vapor pressure as well, that you can mention these three parameters. Thank you very much, Sabina. Well done. So we'll start with the mechanical side, like the separators, in the next slide. But before going there, I want to show you some other parts of the gravity separation services as well. Actually, there are many of them. For example, the flash vessels, slug catchers, HP, IP, or LP separator. Here it's high pressure, intermediate pressure, or sometimes you can see it MP, medium pressure, then low pressure separators. They are as it's known from the name, they are differentiated based on the pressure differences. Then we have treater, degasser, electrostatic coalescer, desalter, compressor, knockout drums, or with the other name scrubbers, glycoamine scrubbers, flare knockout drum, API tanks, we say it. This is also part of separation technique. Then gas flotation units. There are a part of the IGF or DGF flotation units. Also hydrocyclones. So this is just a list of some techniques, but if someone asks you about the gravity separation services, you can mention all of these names, and especially all of these things that you can see, it is both part of the upstream and downstream operations. I mean, in both of the fields, either at the offshore platforms or onshore facilities or at plants, refinery level, you can find out most of these gravity separation techniques, also even a more complex ones. Now we'll talk about, as I promised, the separators part. I'll give some definitions. They are quite useful and it's part of actually technical dictionary. So bulk separation, what does it mean in general, bulk separator? So we'll nail it down, some terminology before we go further. So it is defined as, it is two-phase or three-phase separator. That's that vessel. They are used for initial or intermediary stage of separating multi-phase production fluids. For example, we have the word of bulk, as I mentioned. It tells you this is a coarse separation. It is not just fine polishing. I mean the fine particles. It is bulk. It is coarse separation. It's a big volume. You are removing like a big chunks, the main gas cap, for example, from the liquid in case of petroleum side, in case of wellhead fluid separation. If it's a three-phase unit, the free water from the oil as well. But remember one important point, if it's just two-phase separation, for example, like this, you only have vapor outlet and liquid outlet. If it's two-phase separation for the horizontal, it's the same, vapor outlet and hydrocarbon outlet. When you have additional water separation here, it becomes three-phase separation, okay? It's not two-phase, it becomes three-phase separation. So as I mentioned, two-phase separator, it is just gas-liquid separation from the vessel. So if I mention additional details for your knowledge, the two-phase separators, they are commonly used at every industry, especially in every different parts of units of the oil and gas industry. They just handle the gas and liquid, and as again, you can see here the two-phase separator vertical or three-phase horizontal. If you don't have this outlet water, it's going to be just two-phase separator as well. And the residence time, remember that inside the vessel, it means how long your fluid sits before leaving throughout the valve, throughout the outlet points, okay? That's the residence time definition here. It is not only specific to the reactors. Residence time, we discussed it in the separation as well, because it gives you understanding of the separator design concept, and then to understand if there is any operational problems that would be helpful for troubleshooting, okay? So let me ask you this question then. Imagine that your residence time is too short. What do you think? What could be a result of this? You have very short residence time, and you have to think about what could be its consequence. Yes, Elvin, I was gonna ask you exactly. So we'll not get the sufficient, or let's say the good quality separation, and we'll have a bad separation. Thank you, Elvin. And now the second part of this question. Let's say we have too long residence time. What's going to happen in this case?
Very low liquid level, maybe.
Or we say that it's again another type of inefficiency, and we could get a very, very large vessel. And we don't want to get very large vessels, especially if you are at the offshore, because of the weight limitation and the space limitation. Okay? Yes. Thank you very much, Laman and Elvin, for your answers. Well done. And let's coming back to the third phase separator. We said that we have additional water, and we call it produced water because it is not completely free of the oil, free of its impurities. It is for now called like produced water. And in that case, we say that so the vessel has to stratify into three layers. We have the gas at the top, then oil in the middle, It's actually a mixture of oil and water, and the water, it's going to be at the bottom. And the reason, I hope you all know that the water at the bottom and the oil in the middle, it's the density differences. And as the water is heavier than the oil, the water, it will be at the down, and the oil, it will be at the top of the water, okay? And you have here one element. Do you know the name of this element that helps us to separate water and oil? Yes, Sabina was right about this one. It is called weir. Okay, so this helps us to separate the water and the hydrocarbon phases between each of them. And here, as I said, will be water again, and here the hydrocarbon, or just H and C. Okay, good. And other vessel types, if I say about some standard notes that the same vessels achieving finer, a bit even smaller the separation quality, they are also named by their service types. For example, the scrubbers, coalescers, sometimes polishers as well. For example, the coalescers that I mentioned here as well, the electrostatic coalescer. For the emulsion process, if you know about the oil treatment process, so for emulsion purposes, in order to separate this emulsion, we are using actually the electrostatic coalescer. It is one of the most well-known equipment in the industry. You can also search about it. These are all of them like different variations on the same physical principle based on gravity and phase difference, okay? And but they are optimized for different duties, for different responsibilities. And as a tip, I would like to give you, it is very important. And if you are starting as a graduate or just junior level engineer, you have to ask yourself this question. When you are selecting a separator, your first question should always be that, how many phases do I have? Is it 2 phase? Is it 3 phase? How many phases it's required to separate? And what is required outlet quality of each product for hydrocarbon, for water, for gas? It determines very initial amount of information for starting the design of separators for any equipment. So these answers, they will help you to determine the vessel type, then also internals, then also some parameters of the separation, okay? Later in the phase of the design, it will help you to identify the control philosophy as well. I hope it is clear, and we'll go to the two-phase gas-liquid separation to show you some internals here. So this is the vertical, this is the horizontal one. I have added here the very important video that you can watch it later. It is just introduction. Actually, if you want to see how they are working, like, I mean, what is their working principle, I recommend you to just type on the YouTube horizontal or vertical two-phase, three-phase separation working principles. You will see so many different companies. They are actually selling their products, selling their equipment. That's why they have added many YouTube videos for understanding the concept better. So they are very useful, and I recommend you to go through as well. So going back to the basic principle, we said that if we look at the two-phase separation, the fundamental driver was gravity, phase difference. And when a multi-phase stream enters a separator, we want to give some time for gas and liquid, like some enough time, residence time that we called it, so to be separated. For example, the gas phase, it's gonna be upper side, the liquid phase, it's gonna be at the down part, as you know. They are naturally disengaged from each other based on their density difference for this, or gravity difference, or just phase difference. Horizontal versus vertical. When we see this difference between both of them, you'll actually typically encounter these two different configurations. And the horizontal separators, we say that these horizontal ones, they are very good for, most common for high gas to liquid ratios. And you have like the one inlet on one end and outlets for gas and liquid at other ends. The long horizontal run, it gives like liquid droplets time to fall out of the gas phase. And vertical separators actually here, oh, okay, I lost it. Yes, vertical separators actually here, they are more compact and handle better when you have higher liquid flow rates. When you have liquid flow rates are so low, or when slugging conditions are expected, Depending on some references, it could be actually vice versa. But believe me, depending on the service, depending on the application, you can also change between the applications, between the usages of this. And the key internals, they are making a big difference, I would say. For example, for the inlet device, it's very important when you have either high liquid or high liquid flow rate, you should be able to find out the very good type of the inlet internal, the first inlet device. It could be half pipe or semi type, vein type, or even some coalescers we can put depending on the requirement. But keep in mind that each of different inlet device, they have both advantages and also disadvantages, depending on your service and so what your customer, what your client needs. So you can suggest them different vein types, cyclone, half pipe, semi pipe, and etc. So it's just generally the inlet one. It helps you to break up the incoming flow and it reduces the turbulence for better separation. Then at the gas phase outlet, we have another popular internal device, which is the wire mesh, or it just looks like exactly the same like mesh pad in your kitchens at your homes. It's very the same like type of the material, I would say. It's typically called wire mesh, mesh pad, or sometimes vein pack near the gas outlet. For the vertical I showed, and for the horizontal, it's located here. So it helps you to catch out some liquid fine liquid droplets, not to go with the, let's say, the gas, because I just mentioned when I was answering to Sabina's question, after this line, like the gas line, it's mainly sent to the compressors. And in the compressors, as you know, as part of the working principle, it only works with the gas. When there are liquid droplets, let's say they go into the compressors, it could be detrimental, it could be mechanical failure for the compressors in the long term. That's why we have to make sure that we have put mixed extractor, mixed eliminator, wire mesh, mesh pad, and etc., any name that you can call it. So not to send some liquid fine droplets into the compressor, okay? So next, if we come to the weir, we mentioned it. For the vertical, they have additional, sometimes in the older designs, they have the chambers as well in order to heat some part of the liquid and send it to the gas phase. But in the, let's say, modern designs, it is less frequently seen that. And for the gas-liquid interface, for the outlets, especially, I would say, in all of the separators outlets, for example, the here. So we put some vanes in order to avoid the turbulence inside the separator, and we'll send the liquid outlet to the downstream, the applicability. For example, if we send the only oil and water, maybe at the downstream, it will be oil-water separation, oil treatment, produce water treatment as well. But if we have the third phase, like separately, we'll have the produced water and it will be sent separately to the produced water section. And this part, it will be going through some liquid, oil liquid treatment. Okay. And as a tip, finally, from this slide, there are two most important design parameters for separator. I mentioned the first one, it's the residence time, liquid residence time, I would say. It must be enough, let's say either long enough for gas bubbles to rise out, to disengage from the liquid phase. And the second one is the gas velocity, actually, because gas velocity, it should be kind of low enough for some liquid droplets fall out, disengage from the gas phase into the liquid phase. Imagine that if your gas velocity is too high, like it goes out from the outlet of the gas side, so you will not have any separation and your compressor will be damaged in the upcoming future, let's say, okay? So that's all from the two-phase gas liquid separators. So do you have any question up to this point? Okay, if not, I'll continue. So we come to distillation. I think it's one of the most popular topic that's used to be taught at universities. We now move from mechanical separators I mentioned here. We now move to the thermal separation. The thermal separation I mentioned before, it was the volatility difference, solubility differences. Even we said that the difference in the boiling points, vapor pressures. These are all part of thermal separations. So let's say if separators are just the workhorse of upstream processing, distillation is the workhorse of refining and petrochemicals industry. I would say you can't see any refinery, any petrochemical facility without distillation. You have heard about most probably the CDU video, like crude distillation unit, vacuum distillation unit. They are the heart of refining process, and you definitely have to design, or during operation, you have to definitely visit the distillation in these columns, and you'll get to know many things from this equipment. It's heart of the separation processes, as I said, and the very first and important part of the refineries. So distillation is a thermal process, thermal separation techniques, I said. The core principle is that, I'll not go through all of the details, but I'll say you the main important points. Distillation in general, it exploits the fact that different components in liquid mixture, they have the different boiling points. Or more precisely, we mentioned just different relative volatilities. So different boiling points from the temperature and different vapor pressures of each liquid component inside of mixture, it will bring out different relative volatilities. And when we heat this mixture, so we'll have more volatile component and less volatile component. As you know, the more volatile component, which it is, let's say, tend to leave the column very first. This is the more volatile component from the top, and the less volatile component from the bottom, it's gonna be the heavier ones. Like its density, its specific gravity is too high, and it is really hard to volatile to boil off from the, let's say, the column itself. Okay. So simple distillation, you can also see it during the lab classes. Simple distillation is one vaporization condensation step, and in general, it works well when your boiling point difference between components, it's really high. For example, as a rule of thumb, we said that it's greater than 25, because if you have very, very close one, I hope you know that. So for distillation, when your relative volatility is too close, which comes from the boiling points, when your boiling point is too close, it's really hard to separate it with the simple distillation. Because we say that if they are so close to each other, they could also create the isotropic components. Okay, I'll come up to this point. The next one is the fractional distillation. We say it for the fractional distillation. So actually, I mentioned the CDU and VDU, so crude distillation or vacuum distillation unit. So for CDU, actually, this is fractional distillation because it has more than one, let's say, the different components. Fractional distillation, when components have closer boiling points, we need fractional distillation because there are multiple equilibrium stage stack on top of each other in a distillation column. So the atmospheric distillation of crude oil, it's the, like, as I mentioned, the largest scale one, largest scale example, and a single column, for example, it separates from the top fuel gas, the C3, C4, the LPG, butanes, the naphtha, kerosene, diesel, the residues, and everything. So when you are visiting again the refinery in Azerbaijan or in any other country, definitely ask to see the crude distillation unit, even on the DCS, on the control room, or at the site, that doesn't matter, but you will be really amazed how beautifully and how smartly it is being designed, okay? Coming to the next stage, it's the vacuum distillation unit, which is the part of vacuum distillation unit video at the refinery. Vacuum distillation unit, from the name, you can actually feel that it works at the vacuum condition. Atmospheric distillation column, it works at atmospheric condition. When I say atmospheric condition, it is actually, the atmospheric condition. So it's the same. For vacuum, it's definitely less than 1 bar gauge. Okay, it is for sure less than 1 bar gauge. Vacuum distillation, it reduces the operating pressure below atmospheric, and it will help you to lower the boiling point of all components. So in your opinion, why I have to lower the boiling point to separate the components easier. So my question is actually, what type of components I am sending to vacuum distillation column? Mentioned, we are dealing with in vacuum distillation column, like see at least 30, 40 plus components, hydrocarbons. And as the boiling points are too high, and also their, let's say, the viscosity is too high, in order to make them move, you have to either decrease the pressure, or you have increased the temperature very, very high level. To avoid that, they are using the vacuum distillation columns. And in the vacuum distillation columns, actually, in this way, we will be able to separate at least some part of, let's say, the residual hydrocarbons. And then we can use it, the asphalt, waxes, paraffinic oils, and etc. But they will be really the, let's say, the really heavy type of the components. Thank you. And coming to the last one, which is the isotropic distillation. Why we are mentioning it? As I mentioned, in this simple distillation, we cannot separate like very close ones, very close boiling point ones, because they can produce isotrope. Isotrope, it's kind of mixture. So where we have the vapor and liquid, they exactly have the same composition. So the normal distillation, like conventional distillation, will not work here. So, for example, water ethanol isotrope at 95.6%. So it's the famous example. We have so many examples, but this is the most famous one, I would say. And to break it, you are adding the third component, and entrainer. It will help you to change the relative volatility of each of them in the mixture, and it will help you to separate it, to proceed it. Okay. Another tip from this slide, I would say, if, let's say, someone, your teacher, your engineer, your supervisor says that the distillation column is not meeting its purity spec, like purity point, because we are interested on the on-spec and off-spec product. On-spec, we say that we are reaching the purity point, its intended use. But when they say that this is off-spec, it means that we are not getting the right separation efficiency. There is a problem in the distillation column. That's why we don't get the wanted product. So this is not meeting the purity spec. If they tell you this, it means your first instinct should be to check your reflux ratio and reboiler duty. I'll not go through the same example once again, but we mentioned last time in the case study that Nazrin presented to you, we have to make sure that your reflux ratio and the reboiler duty, they are integrated in a good manner in terms of unit operations, because if you lose in any of the control, let's say you'll have either too much vapor or too much liquid in the distillation column, and you won't be able to get any of the very good product or purities. Okay, so these two variables, especially reflux ratio, I'm mentioning it again, RR, reflux ratio, and reboiler duty, RD. So they will be very useful to find out what's going on the distillation columns. Okay, and in order to understand better the distillation column unit operations, you have to make sure that you understand it in a very good way. Okay, so coming to another big picture, so knowing the different types of distillation, now we'll learn and understand how the column itself is assembled and what each part actually does. So I hope you heard that. So from the feed, we have the upper section and below the feed sections. Then we have additional at the upper side, the condenser, reflux drum. We have the reflux pump. We have the control valve. We have the control valve here. Then we control the pressure. We control the flow. We control the level. We control here those, we don't control, but we get also the analysis of the distillate here at the top product. Then we control the temperature of the whole column with the help of the steam inlet. This is one of the easiest, let's say the simplest way of controlling the temperature in the distillation column. Then we have at the bottom side the reboiler. We have the steam valve, utility valve. Then we have the bottom side control valve. We have the level controller here. So it's actually a very good unit that, so we can understand all of the control systems really, and it will be very useful to you to understand it. And it's how it's happening. It's inside. You can see there are feed tray, there are downcomer. There are actually from each downcomers, it is separated one by one, the liquid and the gas phases. Gas phases are going above and the liquid phase are going coming down. And the liquid phase, as I showed here, that this is going to reboiler, and the gas phase, it goes to the condenser. Okay, what is coming back? It's the reflux, and this comes from actual the reflux drum, some part of it. And some part of the, let's say, stream, the hot stream from reboiler, it's sent back to the column as well. Okay. Now, if we see very quickly, the condenser at the top again, it's the overhead condenser cold, and its job in general is to cool down and the condense the vapor that leaves the top of column, and some of the condensate that we called again the reflux, it will be turned back into the column, because guys, it helps you to cool down some part of, let's say, the cooling down process in order to ensure you have a better mass transfer efficiency, mass transfer between liquid and vapor. And in general, by the way, the condenser itself, it is mostly, always mostly air-cooled type or water-cooled type of heat exchanger. If it's air-cooled type, as you know, it works with the air, but if it's water-cooled type, it works with the cooling water, and this cooling water coming from the outside battery limit of the plant, okay? So if your, let's say, another part condenser can't remove the heat fast enough, that we saw in April case study with Nazreen, your whole column, it's gonna suffer. Coming to reflux drum, the small drum, the other name is like accumulator overhead drum as well. So you can call it how you wish, but mostly reflux drum, we say it. You have the accumulated condensed liquid from the condenser. So from here, the reflux pump that I showed you, it will send some part of, let me take my pointer again, some part of this condensed liquid back to the column. And the reflux ratio that I mentioned in the previous slide, that you have to be very careful. So this is the ratio of liquid returned to the column over versus product taken off. Okay, so this is one of the most powerful, like, operating condition, operating principle you have to handle during your, let's say, the working experience. And the higher reflux ratio actually means it's a sharper separation, and but at the same time you have means higher energy consumption as well. That's why you have to ensure that you are optimizing your condenser duty, your reboiler duty as well. And generally inside you have the trays, or you could have the packing. You have to be very careful in this part because it has been an interview question in the past years. So the contacting device are either trays or packing. The different tray types could be sieve, valve, bubble cap. So based on the different services, based on the different, let's say, purposes we are using, vapor bubbles through the liquid, mass transfer, it's better in the bubble cap in general. But remember one point, structured packing in general achieves the same thing, but structured packing have one important advantage over the trays. In structured packing, you have less pressure drop compared to the tray packing. You can think about like this. For the tray packing, in each tray, you could have approximately 10 millibar, 10-20 millibar. Let's take 10 millibar, let's say, the pressure drop. But for the structured packing, you will have the less pressure drop. So that's why in the vacuum services, actually, we are using structured packing, not let's say the tray packing. But normal crude distillation unit, you will see that mostly the tray ones. But for the vacuum distillation unit, you will see the you will see the structured packing types. So it minimizes in general pressure drop. So coming to the feed tray, during the simulation, like if you are using Aspen Plus, Aspen HYSYS, especially in Aspen HYSYS or Pro 2, for example, so you have to find out when you're designing your distillation column, your feed tray. And this is actually a very special and specific point. It enters at specific location, the feed tray. It is actually chosen where it enters to minimize the energy required for the separation. So above the feed, I call it rectifying section. Below the field, I call it stripping section. For above the feed, for rectifying section, it enriches the vapor in the lighter component. For below feed, I would say that this is stripping, and it strips the lighter component out of the descending ones. You see from the each downcomer, I have the descending liquid. So actually, if you don't get the right location of the feed tray, so in general, your energy saves, it's gonna be really lost. So that's why during the distillation projects or distillation designs, you have to ensure that your feed entry, it's at specific and the right location. Coming to the reboiler. So the reboiler, it's at the very bottom, as you know, it's a column heat source. And we said that it partially vaporizes the bottom's liquid and sending vapor back to the column as well. If you remember, I mentioned during the quiz at the entering part, we had a thermosiphon reboilers. And actually, I mentioned that these are the natural convection type of, and we said that they are based on density difference between boiling liquid and cooling liquid. They are circulating the fluid without a pump. Okay. When we have a kettle reboiler, let's say we don't have thermosiphon, but we have kettle ones, they are even simpler, and they are just, the heat exchanger with vapor space. And we could have also the fired reboilers. They are using furnace, but it is very specific applications for getting very high temperatures. To be honest, in my experience, I haven't seen, but I have heard that there are special types of these reboilers. So as a note, I mentioned 3 of them. Once again, thermosiphon one, second kettle one, and the third one is the fired reboilers. There are even 2 more different types, but I will not mention it today. So the operating variables as a tip finally from this presentation, from this slide, a common trap for the graduates especially. So if you see more stage on the paper, on the PNID, on the PFD, or wherever you want, it doesn't always mean that you have better separation, okay? Because it comes from your design parameters, it comes from your operating variables, how you are developing your operating variables, or how you are operating at your condenser level, at your reboiler level, how you're operating your valves, if there is any problem with maintenance, if there is any problem with your operations. So it really matters. So you have to be very careful. So the distillation top problems like weeping, efficiency losses, entrainment, so jetting, and etc., they don't happen. And in that way, you can ensure that you have very good separation. Okay. And my reference here, it was the American Institute of Chemical Engineers, the paper, and you can also have a look. It's very easily, let's say, explaining everything, and it will be very easy to understand everything. That's all from the distillation. If you have any questions, you can open your microphone and ask, or you can type in the chat. I will go to absorption and adsorption, the final part. So it's another confusion topic, I would say, for especially the young engineers, absorption and adsorption, until you see it in the real life. So absorption and adsorption, I'll let you first of all know the common and important difference between them. That's mostly confused. And the rest, it will be really easy for you. So the names, as I said, sound similar, but the physics are completely different, because absorption, it's a bulk phenomenon, okay? We mentioned the bulk separators, if you remember. We said that it is a very big volume. It is an important, a very big core separation. I don't say you have to confuse it again, but the bulk phenomenon, it means that this is gas into liquid, okay? We don't have any solid at all in absorption, no solid. But for adsorption, you have surface phenomenon. The surface you can understand as a solid. You know, you have a sponge at your kitchens, at your homes. As an appliance, actually, it is adsorption because it has solid surface, okay? This is adsorption. But coming to the absorption, it is gas into liquid one. It is mostly used at refiners in order to regenerate, to clean, and reuse the service, okay? The regeneration purposes, we are using absorption and adsorption columns. Coming to absorption, simply, the gas component transfers from the gas phase to liquid phase, to bulk volume of liquid solvent, and the solute will dissolve throughout the liquid, and it goes into body of the liquid. That's mentioned here. That's what I said here. Think of, for example, the carbon dioxide in water. You know, you are drinking, especially during summer times, the Coca-Cola, Fanta, or the different kind of sparkling waters. For example, the CO2 isn't sitting on the water surface. Okay, it is actually dissolved throughout the liquid. And next time, if you are buying a sparkling water, just turn and look at the different, let's say, the specs inside, and you will see that the CO2 is really dissolved, and you will find of the how much, let's say, milliliter, milligram it's dissolved inside the water. This is, for example, just simple absorption. And I would say the driving force, it's very important. It comes from the Henry's law, and Henry's law describes the relationship that you have the partial pressures of component. They are equal to Henry's constant times concentration of liquid. So it actually comes from P is equal to H multiplied by C. And here the high pressure says that high pressure, remember high pressure, it always favors the absorption because it helps you to solve more gas. Okay, I'll write it as your P is increasing, more gas will be more dissolved. And I would say the high temperature, it is not favored at all for absorption. So it actually, which is why we are regenerating the solvents by heating, okay? We are not favoring it. We just favor mainly the high pressure because it helps you to dissolve more gas in the liquid, in the solvent. Coming to the absorption equipment that you can see on the right-hand side. So this is also a part of the American Institute of Chemical Engineers, the research paper. So I also took the same reference source. So you can see here we have the sour gas. This is actually the not clean one. This is a dirty one that had to be regenerated. So we are also supplying the lean amine solvent in order to treat this gas. From this sour gas, from this lean amine solvent, they will have a mass transfer between them. The sour gas, it will be cleaned out and it will be sweeter gas because its sulfur content will be decreasing, will be lowered. But for coming to the lean amine, which it has the, let's say, the better clean properties, it will be already not clean anymore and it will be rich amine solvent. And we'll send it to the second column in order to regenerate from rich to the lean amine also, okay? So this is all from the absorption. Now I'll give you some information about adsorption, and then I'll also show you the equipment. So adsorption surface, we said that adsorption is a surface phenomenon and it's actually completely different physics. So molecules from gas, even from liquid, doesn't matter, they stick to surface of solid adsorbent, okay? Solid adsorbent. Always remember the sponge at your home, at your kitchens. So here nothing penetrates actually into the bulk of solid and it all happens at the surface of solid. And that's why actually we say that the surface area per gram, it's a critical parameter. You can see it's the meter square over gram. So for the adsorption phenomena, for adsorbents, especially for this purpose. So it's very important. For example, I know for activated carbon, it's actually 1,000 millimeter square per gram, and it's one of the best adsorbent in the industry. There are two types of the adsorption process. It is either physical adsorption or chemical adsorption. Physisorption, we say it, they use the van der Waals forces. But when it comes to chemisorption, they are using the actual chemical bonds. This is high energy. They are often irreversible, by the way, and it limits the how many regeneration cycles that can adsorbent could tolerate, okay? And the common adsorbent, as I mentioned, it's, for example, activated carbon, one of the best, then molecular sieves, zeolites. We see it so much in the petrochemicals facilities. Then we have the silica gel and activated alumina on the catalyst especially, and regenerated by temperature swing, TSA, or pressure swing, PSA, okay? And I'll show you very important industrial applications of this adsorption. You will really like it, and you will learn a lot from this, because in petrochemical facilities, we are actually purifying the hydrogen. We try to achieve the hydrogen purity like 100, very near to 100%, like 99.99999% of hydrogen. So that's why we are using it, and it's very interesting. For example, on the right, you can see this is part of actual adsorption process. It's for example, treating the hydrogen. But before that, I'll give you another absorption industrial example quickly. The first one is amine gas sweetening, then CO2 capture, then SO2 scrubbing. There are many research actually going on for the CO2 capture at universities, and you can see that they are done by the absorption technique. So with absorption, using different zeolites, using different carbon types that I mentioned here. So you can actually find out the solution for CO2 capture. So it could be potential research topic. For amine gas sweetening, we are using the monoethylene amine, diethylene amine, or monodiethylene amine, if I don't mistake the name. But this are the amine solvents in the absorber, and we say that the corrosive, the H2S content, they are acutely toxic, and you cannot send it directly with the pipeline to the customer. That's why you have to, let's say, sweetening this process. Here you are using the mentioned solvents, MEA, DEA, or modern MDEA, and the amine chemically reacts with this acid gases. For example, here I showed you from the sour gas inside H2S and amine content from the top. It will be like the reaction between them, chemical reaction. So they are absorbing it, and the sweet gas, it will always lives at the top, and the rich amines at the down. So essentially, then it will go to the stripper, this rich amine solvent, it will go to the stripper. Remember it, stripper. Okay. And they will be like the heat drives of the acid gases, and the lean amine from the stripper, it will come back here to the column as a lean amine to the absorber. Okay, so actually without that process, without this amine gas sweetening unit, I would say the refinery or petrochemical industry would not function at all. So coming to the SO2 scrubbing, it will be also very quick and easy. It's like flue gas. You have the flue gas desulfurization at power plants, at refiners as well, at the furnaces. They are using absorption too, but they are using a different solvent, especially the limestone slurry solvent, because it absorbs your SO2 from flue gas, and it produces the calcium sulfate. It's like this, calcium sulfate, and gypsum, we call it. As a byproduct, it can be sold for wallboard manufacturing or different purposes. And why we are doing it, actually, the SO2 scrubbing, because there are so many regulations going on right now in the world, in the oil and gas world. The SO2 should not be emitted to the atmosphere. In case of the emission, they had to pay some taxes and some fines as well. So for emission regulation purposes, they are working on some new technologies for SO2 scrubbing as well. It's another research topic idea for you. Coming to adsorption, the most important, and I would say the most popular one, is the H2 purification. So for H2 hydrogen purification, we are using pressure swing adsorption. From the name, you can feel that it is a swing process. It is at the high pressure, low pressure, high pressure, low pressure, activation, deactivation. With this manner, we are achieving the, let's say, the very pure hydrogen. Actually, we say that in the reformer of gas, it contains mostly the hydrogen, like very high part of it, it's a hydrogen, but it has also like CO content, CO2 content, methane content, or some other impurities as well. At high pressure molecular sieves in the adsorber beds, they are selectively capture these impurities. And with the help of this, then this bed is depressurized, as I mentioned. The first one is high pressure, then it will be low pressure because it's depressurized. So here, with the help of this depressurization, the impurities will be desorbed and swept away. So you do the same thing like another HPLP, with this so many cycles. it will be perfect, let's say, result for your hydrogen, because you'll get over 99.99999% purity, okay? And it's very useful, very suitable for example, fuel cells, for hydrocracking, for ammonia synthesis, or I would say use the syngas operation later. It's very, very useful, and you can also find out in most of the petrochemical facilities this hydrogen purification, okay? Coming to last two, it's the molecular safe dehydration. Briefly, they are used actually for cryogenic processes, remember. So, for example, LNG production or NGL extraction, ethylene plants sometimes. We are using here the zeolite beds as an adsorbent. Typically, it is called 3A or 4A. This is special chemical, let's say, the shapes for the zeolites. They are absorbing water to extremely low levels and then achieve the dew points like very, very low, like -70, -90 even sometimes. Then beds, they are regenerated by flowing hot gas through them. And this is actually, again, swing cycles, like temperature is high, below, high, below, high, below. So this is like a TSA cycle, temperature swing adsorption. So the pressure swing adsorption, it was the pressure, but temperature swing adsorption, it's that with temperatures. Again, pressure swing adsorption is for hydrogen, but temperature swing adsorption, it is for cryogenic processes, okay? Ethylene process, NGL extraction, or LNG production, and etc. Lastly, it is the VOC recovery. So for the VOC, finally here, the activated carbon adsorbers, they will help you to capture some volatile organic compounds from the storage vents, from process exhausts. And it will help you, again, to meet your environmental regulations, the specific standards on the VOC. Actually, all of this absorption, especially adsorption, by the way, it helps you to stand with the emission regulations, and they are really popular right now in carbon. They are used for it. Then molecular sieve, we mentioned, H2 we mentioned, but then SO2 scrubbing, flue gas desulfurization, it's another example here, or CO2 capture, another example. So that's all from the absorption and adsorption. Just as a final tip, I would say, when you are making a selection between absorption or adsorption for gas treating duty, just always think about the concentration of component to be removed. For example, how much SO2 I have to remove from the flue gas, how much CO2 I have to capture, how much H2S I have to remove from the amine, or how much purification H2 I have to achieve in PSA, or LNG in TSA, or VOC in with the activated carbon recovery. So you have to think about them. And for absorption, they are handling the higher concentrations very well. And for adsorption, they're actually good for very small, like trace amounts for removal and finishing duties. So that's why you can get, for example, from very low ppm levels to even lower, like the sub ppm levels as well. Okay, so absorption, it is bulk phenomenon. It really removes a lot, but adsorption helps you to remove even further down, but small traces, I would say. Okay. I will say thank you very much for listening. That brings us the end of today's lesson. Takeaway. If you want to take anything from today's session, so the first one, always match the separation technique to the physical and thermodynamic properties of the system. Is it mechanical? Is it thermodynamical type of separation? You have to decide this first. Second, operability really matters as much as your design efficiency, especially we talked about this in distillation column. So you have to understand your failure mechanism, your failure modes before your problems arise. As I mentioned, if you have any issues in the distillation column, first of all, you have to check your reflux ratio and then your reboiled hydrocarbon back to the system, your reboiler duty. And the third one, we said that the separation is never, ever truly complete, because every technique, they have some limits. So you know that it will allow you to design the even robust processes more. That's all from today's session and the key takeaways. So after this, we'll complete the quiz from this session. And thank you very much, and see you all in June technical workshop again.